with yours truly, Professor Mimi Rasky. A quick overview of the course. We're going to be learning computational modes of thinking, and you're going to gain some skills in the art of computational problem solving, which will involve some logic, and you're going to be able to make computers do what you want them to do. Notice the word computation appears twice here. What does that mean exactly? Well, it will mean that we are going to be using mathematical objects that represent a collection of questions that a computer might be able to solve. For example, factoring a number. Or maybe, let's say you have 20 people over at your house and you want to find out what the probability is of two of the people sharing the same birthday. That might be kind of interesting. And you could get the computer to do that for you. Stay tuned, and after this video you're going to be taking a short quiz. Here are some questions that you might want to pay attention to. What are the two types of knowledge, and which type of knowledge is typically used in a computer program? Number 2, what exactly is an algorithm? And is a linear search an algorithm or not? Number 3, what is the difference between a low-level language and a high-level language? And is assembly language considered a low-level or a high-level language? Number 4, can you give at least 3 examples of a high-level programming language? Is Java considered a high-level language? Number 5, what are the 5 steps of the programming process? And which step is the one that students are most likely to skip? Which step is the one where students tend to get stuck? And number 6, will you always get an error message to tell you what's wrong while you're troubleshooting? And what's the difference between a syntax error and a logic error? Okay, let's take a look at the types of knowledge. Computers know what you tell them, and there are 2 types of knowledge. Declarative knowledge is statements of fact. Here's an example. Suppose I told the whole class that there is a candy taped to the underside of one chair. This is declarative knowledge. It would be some fact. The second type of knowledge is known as imperative knowledge, and that's more of a recipe or how-to knowledge. In this case, how to locate the candy. This is where computers can be very helpful. For example, to find the candy, we could use the following recipe. First, I could face the students at the front of the room, count up the number of rows in the room, and start from the classroom's left-hand side in row 1. And I'd count to the right 1 chair, and I'd ask the student sitting in that chair to reach under their chair and look for the candy. And if the student finds the candy, stop. Otherwise, count to the right 1 more chair and repeat. Ask that student, for example, to look under their chair. And keep going, and after that row is complete, if the candy still hasn't been found, move on to row number 2 and keep repeating. Now, this is a very simplistic type of search algorithm, and it is known as a linear search, or sometimes called a sequential search. Is there an alternative recipe we could use to locate the candy? I'm not going to answer that question now, but think about it for a while. Now, what is a recipe? Well, it's got 3 pieces to it. You've got the sequence of simple steps, and it's also got a flow of control. And that's a process that specifies when each step is going to be executed. And it's going to be able to determine when to stop. You know, it's going to have to give us a way of deciding when the algorithm is complete. Now, taking all of these 3 pieces together constitutes an algorithm. More on algorithms. Take a look at this little comic I found from the internet. This is a number line, and starting at the left, you get less complex algorithms, and as you go further to the right, more and more complexity here. And in another class, your second semester of computer programming, you will actually find ways of measuring algorithms and their complexities. And you can even get a feel for this just with some math classes you've taken. I'm sure that you could appreciate that arithmetic, 2 plus 2 equals 4, has much easier algorithms than, say, algebra, where you have to solve a quadratic equation, for example. I just like this one because the furthest out is a sprawling Excel spreadsheet built up by over 20 years by a church group in Nebraska to coordinate their scheduling. Hilarious. An algorithm is a set of well-defined steps to completing a task, and the steps in an algorithm are performed sequentially. A computer needs the algorithm to be written in machine language, and machine language is written using binary numbers. Now, what are binary numbers? Well, the binary numbering system, which is base 2, only has 2 digits, 0 and 1. And we use base 10, if you're normal, and those numbers are 0 through 9, 10 different numbers. But in base 2, which is the only base a computer understands, you have 2 digits, 0 and 1. Sometimes software engineers refer to this as off and on, 0 and 1. And the binary numbers are encoded as a machine language. And each CPU, central processing unit of a computer, has its own special machine language, and these are just 3 different examples of different microprocessors. And that's kind of where the problem is that each microprocessor has its own machine language. Here's an example of a machine language instruction. Look at all these 1s and 0s. That'd be pretty tough to program in machine language. I don't know if you'd want to do that. I got to say, though, I've done it when I used to be an electrical engineer, and it's a little bit difficult to troubleshoot. Let's talk about assembly language. And we are going to talk about machine language more in our next video about hardware. Assembly language. Well, in the distant past, programmers wrote programs in machine language, but that was kind of difficult, as you can imagine. So the programmers developed a slightly higher level programming language to make things easier, and the first of these was assembler, also known as assembly language, which takes the 1s and 0s that we saw on the previous page and converts it to a low-level language known as assembly language. And assembler made things easier, but like I mentioned before, was very processor dependent. And just to give you a little flavor, here's an example of some code in assembly language. Yikes, that looks pretty primitive, doesn't it? Well, I want to tell you, if you are a computer science major, right after this class you can take Math 230, and in that class you will learn how to program using assembly language. And, of course, only tough guys program in assembly language. Well, after assembly language, some higher-level languages were written, and they're not processor-dependent, thank goodness. And they allow you to use a vocabulary of reasonable terms, not 1s and 0s. However, all computer programs ultimately are converted to machine language. Machine code is the most basic set of instructions that a computer can execute. Now, currently there are over 2,000 high-level programming languages, and I don't know anybody who knows them all, but Java is one of them, and it's very popular. But here's a list of some more common programming languages, and some of you may even take some of these or have taken some of these. C is one that I used to teach, but we also teach that here at Engineering 120. And Python is up and coming.